All right, so now what we're going to do, and we're going to continue with this rates of change and these applications that we're going to look at. Now, traditionally, and I will say that I definitely know that this particle motion problem prior to last year had been on a free response, had been a type of a free response question for several years prior to last year. Now, last year, the students took two different versions of the AP. Half of the students last year took the main form, and then we had an alternate form. I know that on the main form, I don't believe there was a particle motion problem, but there may have been one on the alternate form. So it's been traditionally a fairly popular type of free response question. So we're going to kind of talk about that in particular because I want to prepare you for every kind of free response question that you're going to see. All right. Now, so we're going to have a motion problem. They're going to definitely, pretty much everything in calculus about rates of change. But one of the things they like to do is this idea of where you're going to be given a position function. And again, this was Newton's motivation for inventing calculus to begin with, because he was looking at the motion of different things and trying to look at their rates of change and their acceleration. It was an application problem. All right, now some terminology. We've been talking about this all along, so they're just making sure that everybody is kind of straight. That the S of t, that is going to be our quantity function, all right? And our quantity is referring to a position, whether that's going to be the height of a ball, whether that's going to be the position function doesn't actually have to be position. It could be the quantity of something as well. But it also could be position in that we're going to be like how far we are horizontally left or right from the point 0 on the number line, or vertically up and down from the origin on the y-axis. So we can have all sorts of position functions that we're going to be looking at. All right? Distance traveled from a certain position kind of idea. And that if you were to take the first derivative of that, our v of t is going to be the derivative of your position function. V of t is your velocity function. Your velocity is how fast the particle or the object is moving, and that's your derivative. And so the velocity function is the first derivative. And then we're going to introduce that there could be a second derivative. That if we were to take the derivative of the velocity function, also known as the second derivative of the position function, we would get our acceleration function. How fast, or how is the speed changing, increasing or decreasing? And that talks about whether or not the original position is either increasing at an increasing rate, that's accelerating, or decreasing at a decreasing rate, maybe it's decelerating, all right? So we have different combinations. I mean, the function itself could be either increasing at an increasing rate or a decreasing rate. So you could be having a function that's increasing, but either slowing down or speeding up. There are different things that we're going to be looking at that we want to be cognizant of in this problem. All right, the next terminology that we want to define for you is displacement. Displacement is basically your change in y. Your change in position is what you're looking at. So our formula for that, because it's the top half of the slope formula, is going to be your plug in b, your end of your endpoint interval, plug in a, and calculate your difference in your y values. That's your displacement, difference in your y values. All right? Now, distance traveled. This is kind of important to recognize that distance traveled and displacement are not the same thing. The distance traveled, because remember that your velocities can be positive or negative. You can be traveling forwards or backwards, okay? So your displacement is, I have a certain starting position, I've traveled forwards and backwards several times, and then I stop and I want to know how far am I from my original starting place. That's a much different question than if I want to know the total distance that I have traveled. All right? And this one's a much harder problem to do, because I have to know for what times was I traveling in the positive direction, which times was I traveling in the negative direction, and I need to add up the absolute values of those distances. Because your position that you're in has something to do with which way are you moving. Are you moving left or are you moving to the right? Okay? So depending on your velocity, basically you could be moving back and forth and back and forth and back and forth and really racking up a total distance traveled, but yet end up in exactly the same spot you started with, so your displacement is 0. All right, so you basically figure out how far you traveled left and then stopped, turned around. That's your resting point. Traveled to the right, stopped, turned around, and so on. And you have to basically add up your distances. Now your position, because your position function is going to be positive when you are on what you're going to consider positive side of something. So maybe on the right side, if you move to the right, your position is going to be positive. If you move to the left, from your starting position, your position would be considered negative, right? And so we want to do absolute value because even though we might be on the negative side of our position, we would like to know how far, and that's a distance, which is absolute value, right? Our average velocity doesn't change. It's everything we've been doing before. Our average velocity, change in y over change in x, slope of your secant line, change in y over change in x. Your instantaneous velocity is going to be your derivative, your slope of the tangent line, how fast you're going at any given instant, how fast the particle is moving. All right, then we start talking about our difference between the words velocity and our speed. Velocity is speed with direction. Okay, velocity will be positive, moving in the whatever you're considering to be the positive direction. Velocity will be negative if you are moving in the negative direction. Okay, you might decide that going right is positive, going left is negative. Your speed is the absolute value of your velocity, because speed only has to do with how fast, not in a certain direction. Because you could be going 50 miles per hour forward or 50 miles per hour backwards. Your speeds are the same, but your velocities are opposite of each other, okay? So this is an important fact to recognize, and that's kind of a commonly missed problem on the AP that's mostly a reading failure, because they're going to ask you questions about the speed, and you'll forget that you're supposed to remember that speed is the absolute value of velocity, and you'll be answering the question basically thinking about velocity when you really should be thinking about the speed. So it really does make a difference, and you want to make sure you very carefully say, am I talking about velocity or am I talking about speed? Does it have direction, or is it only the magnitude that I'm worried about? All right. Now, let's talk about this idea of speeding up versus slowing down. All right. And so the idea is that we're trying to kind of figure out how the velocity function, your acceleration function, and your speed function. I mean, because technically this is a speed function. Your speed function is the absolute value of the velocity function. All right? And that idea of knowing what's happening with your speed, what's actually happening with your velocity, and how this acceleration, velocity, and how they're all related to the original function is going to be important. Now, we already know that if I had my position function, if s of t is increasing, then that means that my velocity v of t is positive, right? So we have that down. We know that if s of t is decreasing, that means my velocity function is negative. So we have that. Okay? If I have my position function, s of t is concave up, that would mean that my velocity function is increasing, which would then mean that my acceleration function, which is the derivative of velocity, is positive. Okay? So just putting some facts down that you should know. 1, 2, and 3. All right, let's put number 4 in. If your position function is concave down, that means that your velocity function is decreasing, which would mean that your acceleration function is negative. Okay? So those are all things that we've already talked about the relationship between the original function, the position, its derivative, the velocity function, and then What do we know about if we know the velocity function is increasing or decreasing? What does that tell me about the acceleration and about the original function? That we kind of get a twofer on that one. But then they'll start asking you questions, and then this is what this next little section is about. That these are talking about that, what are we doing? What's the speed doing? Okay, based on this information that I have over here. And so the idea is that you really can't determine what the speed is doing unless you know something about velocity and acceleration. Think of it this way, okay? Because speed doesn't really have direction. That, let's think about this first case. We have a positive velocity, okay? So we have a positive velocity, and we have a positive acceleration, okay, at a certain point. So whichever direction I'm going, so I'm going in the positive velocity direction, and I'm accelerating in the positive direction. So the way that I'm headed, okay, S of t, let's think about what we have here. Okay, S of t, your position function is concave, well actually I should do increasing first. Your position function is increasing because of the positive velocity at an increasing rate. Okay, so my position is changing. It is increasing. I am moving in the positive direction at a increasing rate. What do you think my speed is doing? Can you see that they're helping each other there? I am increasing at an increasing rate. So the positive, the velocity, and the acceleration, they're going in the same direction. So therefore my speed is speeding up. All right? But now let's look at the second case. So this was the first case. That was this one right here. Oh, circle that one. But now notice that it gives a second option. It says speed is also increasing if both the velocity is negative and the acceleration is negative. Now let's think about what that means. I wish I'd given myself more room here, but we'll squeeze it in. So velocity is negative. So I have a negative velocity at this point, and then I have a negative acceleration at this point. So what I know, what's happening on S of t is decreasing, and because it's decreasing at a decreasing rate, decreasing at a decreasing rate. Decreasing at a decreasing rate, decreasing at a decreasing velocity. Do you see that they're both working together there? I'm headed in the negative direction, and I'm headed in the negative direction at a more negative rate because it's velocity, right? Velocity, I'm speeding up. When I say that I have a negative velocity, I'm speeding up in the negative direction. So the fact that I'm headed in the negative direction and the acceleration is in the negative direction, I am still speeding up. I happen to be speeding up in the negative direction, but I'm still speeding up. And that's the key here. Okay? So when velocity and acceleration work together, you are speeding up. But when velocity and acceleration are opposite of each other, they're acting against each other. I'm headed in the positive direction, but I'm slowing down. Then your speed is decreasing. Okay? And same thing, if I'm headed in the negative direction but I'm speeding up, my speed is still decreasing because I'm heading one way and I'm putting the brakes on in the other way. So they're acting against each other, so your speed is decreasing. Right? Now, they're going to be asking you questions based on this. They'll basically say, what do you know about the speed at this time? You have to remember that that's a different question than talking about the velocity at that time. Talking about the velocity, I'm just looking at the derivative. Talking about the speed, I have to look at whether velocity and acceleration are working together or working in opposition before I answer that question. Okay? And again, these last two are just kind of reminding yourself that if the velocity is positive, your position function is increasing. If your velocity is negative, your position function is decreasing. And if your acceleration is positive, your velocity is increasing, your position is concave up. And your acceleration being negative, your velocity is decreasing, and your position is concave down. Okay? And so we really want to get straight in our head how all of these concepts work together. All right? Now, the rest of this set of notes is going to basically look at examples, and remember the rule of 4. We're going to have one example where I'm going to give you a formula. So we're going to work at it from the algebraic perspective. And how do I examine all these characteristics given the algebraic perspective? All right? Example 6, what I'm doing, I'm going to give you a graph. We're going to look at it from the graphical perspective. But in example 6, I'm going to give you the position functions graph. Now that's going to be important because there are several graphs I could give you. I could give you the position graph, the velocity graph, a speed graph, or an acceleration graph. And you're going to have to really pay attention to which graph I have given you when you are answering these questions. Okay? Then we're going to flip over here to example 7. So example 7, we have a velocity graph. So I'm still looking at it graphically in my rule of 4, but I'm giving you the velocity graph, which means that we're going to have different conclusions from this. All right? And then the next example that I do, I'm going to give you a table of values. So there I'm looking at it numerically. Now, numerically, I could give you a table that has the position data in it. I can give you a table that has the velocity data in it. I can give you a table that has acceleration data in it. So in all of these situations, you're going to have to be very, very careful about what you're given. Are you given a formula for position, for velocity, for acceleration, or speed? Are you given a graph of position, velocity, acceleration, or speed? Are you given a data table for which of those 4? And then you're going to have to use the information that I've described to answer the questions. Okay? And then we're going to finish out these examples where we're playing around with this interpretation and understanding what's going on with a little economics example. We're going to talk about marginal cost, marginal revenue, marginal profit, and our average cost. And this is all a calculus concept that if you have not taken the economics unit, it's something that you will talk about in the economics unit. However, they will kind of gloss over the calculus part of it, but because we're in calculus, we're going to include that as a discussion here. So I'm going to stop this video here because what I want you to do is we're going to kind of come together and we're going to work through. We're going to have you kind of working through some of these examples and trying them on your own, because I think you're going to learn the most from not me just talking at you about this, but from you working together with your group mates in class working through these examples. I will probably put up some keys to these eventually so you can kind of see the work that I have working through it. But I'm going to have you do, before you come to class next time, I want you to try, we'll just start with, this is the easiest one, example 5. So I want you to look at example 5 and try to answer the questions that are here. Now, it's not about the answer, okay? If you are going to find displacement, you need to show how you found displacement. Show what formula you used. You're going to have to show units, and I would like you to interpret your units as well, or interpret the item that you found. What is it that you actually found? So you're going to do that for each of these. You're going to show your work for finding it, give your units, and then give some kind of what does it mean thing over here. So that way we can really kind of cement all of these descriptions that we have up here that you need to really get down. I don't know if you want to make some flashcards or something to kind of get this stuff you need to have memorized. These are important facts that you have to have, important relationships in application problems that you really need to get down. So spend some time, make sure you basically memorize these before next class, whether you're using flashcards or how you're going to do it. And then I want you to try example 5 and we will discuss it in class next time.